optical rotation and enantiomeric excess. Have you got it? This short video quiz assesses your ability to work with equations relating to determinations of specific rotation and understand the relationship between specific rotation, optical purity, and enantiomeric excess. The quiz consists of 3 questions. It's meant to be taken after you've studied the material and think you understand it. During the presentation, you'll be asked to pause the video and at least try to solve the problem yourself and only then to continue. It won't be hardly as effective if you jump to the solution immediately. Okay, here we go. Number 1, fill in the blanks below. Pause the video while you answer this question. Just read it through and see if you can fill in those blanks, and then we'll read it together when you're ready. Okay, here we go. In an optical rotation measurement, we always use a cell with a standard length from one end to the other. This is because the measured optical rotation alpha is proportional to the amount of sample that the beam of light passes through. This distance is generally 2 decimeters, where a decimeter is 10 centimeters. Similarly, the more concentrated a sample is, the more sample there is, and the observed rotation must be divided by the concentration, C, in grams per milliliter, and the path length in order to get the observed specific rotation, which we write as alpha D observed. When we divide the observed specific rotation by the known specific rotation for the pure enantiomer and multiply by 100%, we get what we call the optical purity, also called the enantiomeric excess. 100% EE means all one enantiomer, and 0% EE means a 50-50 mix, also called a racemic mixture. All right, ready for number 2? Number 2. You go into the lab and do the following reaction, purifying the product using recrystallization. NMR spectroscopy and gas chromatography indicate that your purified product is greater than 99.9% pure 3-phenyloxyurane 2-il-methanol. After doing some measurements, you determine that the specific rotation of your product is minus 49 degrees. If the known specific rotation of the pure RR enantiomer is 50 degrees, what is the enantiomeric excess for this reaction? Which of the 2 enantiomers shown on the right was the major product from the reaction? And what do you think? Could this process be patentable? Worthy of the Nobel Prize? All right, pause the video while you answer this question, and we'll get back to this in a minute. Okay, here we go. Okay, what do we got here? Our specific rotation of the product is minus 49 degrees. That's our alpha D observed. The known specific rotation, that's alpha D, of the pure RR enantiomer is 50 degrees. What's the enantiomeric excess for this reaction? All right, so the enantiomeric excess is defined as the observed rotation divided by the known specific rotations times 100%. Now these are for the same enantiomer. So what we have here is a minus 49 divided by minus 50. In other words, we got the SS enantiomer, not the RR, times 100. And that's 98%. Okay, now, last part of this, which of the two enantiomers shown on the right was the major product of this reaction? Okay, the key here is that because the pure RR enantiomer has a specific rotation of plus 50 degrees, and we got minus, that must mean that we got the SS enantiomer from this reaction. Now, which one of these is SS? Well, all we have to do is figure out one of these stereochemical designations. Let's go for this one right here. It looks like the easiest one to me. Oxygen is 1. This chain that has an oxygen is 2. And the phenyl ring is going to be 3. So we go 1, 2, 3, and you can see we're going in front of the H to get up to this oxygen, which is in front. So clockwise, H is behind, this is R. So this must be the RR, and this must be the SS, and what we got was B. Got that? Okay, challenge. A pure enantiomer X has a specific rotation of minus 10 degrees. You carry out a reaction that gives a mixture of enantiomers of X, and you purify the product. You prepare a solution of 0.2500 grams of X in methanol in a 25 milliliter volumetric flask. After thorough mixing, you fill a 20 centimeter polarimeter cell with 15 milliliters of that solution. After thoroughly mixing again, you record the optical rotation as plus 0.160 degrees. What is the percent EE for this reaction? And what is the ratio of minus X to plus X in this product mixture? All right, think about that. See if you can do it. Come back. All right, here we go. What do we know? Pure enantiomer has a specific rotation of minus 10 degrees. So alpha D equals minus 10. You carry out a reaction that gives a mixture of the enantiomers, you purify the product, you prepare a solution of 0.25 grams of X in methanol in a 25 milliliter volumetric flask. So our concentration here is 0.2500 grams per 25.00 milliliters, and that is 0.0100 100ths gram per milliliter. All right, after thorough mixing, we fill a 20 centimeter polarimeter cell. Remember what a decimeter is? It's a tenth of a meter, centimeter is a hundredth of a meter. So there's 10 centimeters per decimeter. Our length is 2 decimeters. This is a standard cell. Okay. It takes 15 milliliters of that solution, but you know what? We don't care. That's not a piece of this equation. After thoroughly mixing again, you record the optical rotation as 0.160 degrees. Alpha is 0.160 degrees. What is the percent EE for this reaction? All right. Well, what we have to do is get our alpha D, our specific rotation, observed, and that's going to be our alpha, our rotation that we did observe, divided by the concentration and divided by the path length. Okay, so this is our 0.160 degrees divided by 0.0100 and divided by 2. And that's not so hard to calculate in our head. That's 0.16 divided by 0.01. That's 16 divided by 2 is 8 degrees positive. Okay, so the question is, what's the percent EE? Percent EE is our observed rotation, 8 degrees, divided by the specific rotation for this enantiomer, which would be plus 10 times 100%, and that is 80% EE. All right? And What's the ratio of minus x to plus x in this product mixture? Well, the way you think about this is that we have 100% and there's an 80% excess of one over the other. So 80% of this is pure. That leaves the other 20% a 50-50 mixture. And that means that what we have of the one enantiomer is 90%. Rotation is minus of the minus enantiomer to 10% of the plus enantiomer. So the ratio is 90 to 10, or 9 to 1. There you go. Yeah, these are a little tricky. Remember, though, a measurement of optical rotation can tell us how much more of one enantiomer than the other was produced in a chemical reaction, the enantiomeric excess for the reaction. Also called the optical purity, the percent EE can be calculated if we know the known specific rotation of one of the enantiomers, which is the rotation found for a 1 gram per milliliter solution of the pure enantiomer using a 1 decimeter polarimeter cell. Using our measured optical rotation, alpha, and factoring out the concentration of the sample we used for the measurement and the path length of the cell, we can calculate the observed specific rotation as our measured optical rotation divided by the concentration and also divided by the path length. Furthermore, comparing our observed but known specific for one enantiomer, calculate the percent EE as the ratio of those two times 100%. Finally, we can use the enantiomeric excess to report the ratio of the two enantiomers in our product mixture, now that we know how much more of one than the other we have, and considering that taken together, they have to add up to 100%. The enantiomeric excess is a very important parameter for judging the success of a reaction that produces a mixture of enantiomers. A finding of greater than 99% EE means the reaction was highly selective, producing essentially only a single enantiomer. A finding of 0% means there was no selectivity at all. A 50-50 mix of enantiomers, a racemic mixture, was produced. All right, hope you find that was helpful, and I hope you've got it.